So in this lesson, I'm going to take what you have learned about molecular geometries and electron domain geometries, and I'm going to expand it to include 3 new concepts. And the first concept is hybrid orbitals. Now, hybrid orbitals allow us to understand how exactly the shapes that we've seen, the molecular geometries and electron domain geometries, how exactly they form. And so what exactly are hybrid orbitals? Well, hybrid orbitals are the atomic orbitals of an atom, and normally we're talking about the central atom, that mix to form new orbitals. So they're mixing together to create these hybrids, these combinations of atomic orbitals. So if you look at CH4, the valence electrons for carbon come from an s orbital and then 3 p orbitals. And so as a result, those 4 orbitals are going to combine together to form 4 hybrid orbitals, sp3. And so if you're given CH4 and you're asked what hybrid orbitals form to produce CH4, you would say sp3. So in the previous slide, I explained the concept behind hybrid orbitals, but you don't actually need to know the concept behind it so much as you need to be able to predict what hybrid orbitals are going to form when given a specific molecule. So what you need to do is you first need to draw the Lewis structure. And so for SO3, that's an example of resonance. And so the way I would draw it would be as follows. Okay? The next thing you need to do is determine the number of electron domains. So SO3, since there are 2 single bonds and a double bond, that's only going to be 3 electron domains. And then based on the number of electron domains, you need to specify the hybrid orbitals needed in order to accommodate those electron domains. So in this case, since you have 3 electron domains, the hybrid orbital would be sp2 because that takes care of the 3 electron domains. If instead you had 4 electron domains, like in the previous slide, it would be sp3. If instead you had 2 electron domains, it would be sp. And then if you had 5 electron domains, notice sp3, you can't go above 3 for the p because there are 3 orbitals. So then you would go to the d. So it would be sp3d for 5 electron domains. The next concept I'm going to be talking about, we talked about single, double, and triple bonds, but there are actually different bonds that are involved in those single, double, and triple bonds. First, you have sigma bonds. Now, sigma bonds form when you have an overlap of 2 orbitals, and I'll show you a diagram in just 1 second. Pi bonds actually result from a sideways overlap of p orbitals. They don't actually directly overlap one another. And so here are 2 diagrams. The one on the left shows the sigma bond. Notice that they are directly overlapping each other, while for the pi bonds, that results from that sideways overlap, not a direct overlap, of the p orbitals. So since there is a direct overlap for sigma bonds are stronger than pi bonds. Now for determining when you have a sigma bond or when you have a pi bond, it's actually really easy. If you have a single bond, you are simply going to have 1 sigma bond. If you have a double bond, you will have 1 sigma bond and 1 pi bond. And if you have a triple bond, you are going to have 1 sigma bond and 2 pi bonds. So it's really nice and easy to predict what types of bonds you're going to have when you have multiple bonds. The last concept I'm going to go over is the confusion that can result if you're not sure how exactly to draw your Lewis structure. And the concept that helps us quite a bit is this concept of formal charge. Now, the official definition of formal charge is the charge an atom would have if all of the atoms in the molecule had the same electronegativity, meaning they're sharing their electrons equally. Now, why exactly does formal charge matter when we're drawing Lewis structures? Well, the dominant Lewis structure, meaning the Lewis structure that is going to exist in the greatest amount, or has the greatest likelihood of existing, is the one whose atoms have the formal charges that are closest to 0. So if you're comparing 2 different Lewis structures and one has atoms that have formal charges that are closest to 0, that is going to be the dominant structure. The second rule is that a Lewis structure in which a negative formal charge resides on a more electronegative atom, that's going to be the one that's dominant. So those are two rules. Number one is the most prevalent rule, but for number two, just knowing that if your formal charge is negative, it should be on the atom that is more electronegative, the one that's hogging the electrons the most. So let's learn how to actually calculate formal charge. To calculate formal charge, all you do is you take the number of electrons that are assigned to the atom, and you subtract that from the number of valence electrons. So how exactly do you determine the number of electrons that are assigned to an atom? Well, it's quite easy. All unshared electrons, meaning non-bonding electrons, those count as 1 electron each. So if you have a pair, that would be 2 electrons that are being assigned to the atom. If you have a bond, like a single, double, or triple bond, you take half of the bonding electrons. So if, for example, you have a single bond that's 2 electrons being shared, so that only counts as 1 electron that can be assigned to the atom. So if you look at the example of carbon dioxide, here's where the issue rises. There are 2 different ways of drawing carbon dioxide. You could have 2 double bonds, or you could have a single bond and a triple bond. You don't know which one is dominant. However, you can figure that out really easily. So the first thing that you need to do is determine the number of valence electrons for each of these atoms. So that's easy. Oxygen has 6, carbon has 4. There you go. Okay. The next thing that you need to do is determine the number of electrons that are assigned to the atom. So if you look at this first oxygen on the left-hand side, it's got 4 lone pairs of electrons, 4 electrons that are not shared, and then it has a double bond. Remember, each bond only represents 1 electron because we halved the 2 electrons that are being shared. So for that oxygen there, the double bond represents 2 electrons, therefore it has 6 electrons on it. That carbon has 2 double bonds, so that's a total of 4 electrons, and then the oxygen on the other side has 6 again. The next Lewis structure, that oxygen on the left-hand side, has 6 lone electrons, and then 1 single bond, which counts as 1 electron, so that is a total of 7 assigned electrons. The carbon has a single bond and then a triple bond, so that's 4 electrons, and then the oxygen on the other side has 2 lone electrons and then a triple bond, so that's a total of 5 assigned electrons. So you're going to take those values and you're going to subtract. And what you notice for the formal charge, the Lewis structure on the left-hand side has an overall formal charge of 0, while the one on the right-hand side has a formal charge of -1 and +1. So that tells us that the Lewis structure that's on the left-hand side, that is the dominant structure, and therefore we know that carbon dioxide exists like that with 2 double bonds instead of a single bond and a triple bond.